The purpose of this video tutorial will be to show Agile tendon design in Adapt Floor Pro 2017. We're going to go ahead and launch an example here using Floor Pro only. We're not going to use Edge or Mat or any of the other functions available within Builder 2017. We do want to use the RC and PT design scope. We'll go ahead and select OK to open the program, and we're going to be using the tendon toolbar for this example in order to initiate the optimizer. And to build the model, we're going to use the floor wizard for this example. So we'll go to Build Floor Wizard, and we're going to say there are two spans. The spans will be 32 feet in both directions, so we have symmetry about both of the axes down the center of the slab, and the column size will be 20-inch square columns. Slab thickness we're going to be using is 8 inches thick. We're just looking at one level, considering just one floor in this example. We'll go next, and we're going to increase the live load to 60 psf for this example, and we'll say next. The story heights for top and bottom floors will be 10 feet. And in order to have a basis for which we want to improve the tendon modeling or the tendon design, we need to start out with something in terms of both banded and distributed tendons. So we'll go ahead, and for the distributed direction we're going to use a pre-compression of 125. Same for the banded direction. The effective force we'll be using is 27 kips, and we're going to assume a CG of 1 inch in both directions. The number of strands represented by each line in the distributed direction will be 1. So each tendon equals 1 strand in this case. And it's important to note that when we create the tendons using the floor wizard, or if we manually create them, this is just a starting point that we want to use in order to design the slab for the PT. So we'll go ahead and select End. The program will then produce the model. And notice that on each side there is a cantilever that the program defaults to when we use the floor wizard. So we'll review one of the distributed tendons here. We're going to optimize the slab in the X direction, in the distributed direction for this example. Each of the tendons has the same shape, and number of strands again is set to 1. So you can see here we're using a 1/2 inch diameter strand. It's unbonded. In terms of the system that we're using, the effective force we said was 27 kips. The shape is shown like so. We have cantilever down shapes on the two end cantilevers, and then reverse parabolic shapes for the two interior spans. So that is the typical shape of the uniform direction. Now, if we go ahead and we're going to analyze the slab, and we're going to evaluate the slab for stresses for the service condition. So we'll go to FEM. I'm going to mesh the structure. We're going to ignore the strength condition for this example. We're only trying to meet the serviceability requirements for PT. And so we'll go back to FEM and analyze, and we're going to analyze up to the total service level. So we'll limit it also to the service total condition, and we'll run the analysis. And this is a prerequisite to being able to use the optimizer. We have to have an analysis that is up to date, that gives a current status of the design strips for the floor. And we'll go ahead and say yes. Now the second step will be to generate the design strips and to design those strips. So we'll go to Strips, Generate. We're going to regenerate the tributaries and the design strips, and we can see for the X and the Y directions we have design strips in both directions. We're again focusing on the X direction, the distributed direction. The banded direction would be similar in how we use the optimizer to design the slab. So once we have the design strips in place, we'll go back to FEM and design the design sections. So using the result display settings dialog with these different menu items for display, we can see that for design sections, if we turn on for service total, for example, the top stress, we clearly have an overstressed condition here at each of the interior supports, and that's on both faces of the support. So we have 379 is our allowable. We're at 805 at these two end conditions. So 805 at the top, 832 at the bottom, and then at the middle we have a stress of 1049. For the bottom stress, we can see that on either side of the center line in the Y direction, we have a overstress of 514, and if I turn on the numerical display for the support line, it's 503. So roughly speaking, it's symmetric in terms of the results for either span, 529 versus 524, 488, and 536. And some of that difference can come from the meshing and just the differences in how the finite elements are solved for when we have an unsymmetric mesh. So in this case, we're using a sparse mesh, and we have symmetric design results, so we can get slight differences in the results. But what we want to do now is use the optimizer to design the slab. And one thing that's important to note is that the optimizer is used on a span-by-span basis. So we're going to optimize using the optimizer on the interior spans, not the cantilevers. We're going to optimize span 1, span 2, span 3, and then 4, 5, and 6. We really, because of the symmetry, we really only need to optimize span 1, 2, and 3. And if we apply those changes to the entire line of tendons, those will be reflected over here on this side as well. So when we optimize on a span-by-span basis, the optimization takes place due to the geometry and the different requirements necessary to meet the parameters for that particular span. However, when we rerun the model with the new tendons in place, those tendons are considered in the global model from a finite element perspective. And so we want to first illustrate that concept in this model. So we'll go ahead and just close the result display settings. I'm going to refresh the view of the tendons, and we're now going to optimize. So I'll go to optimize. When I open the optimizer, we'll go directly to settings. We want to optimize this slab based on a selected group of tendons, but the desired ranges that we want to use are for pre-compression. Load balancing is 50 to 100. We know that when we optimize this particular example, we're going to have a load balancing that might be slightly over 100, so we'll increase that to 125 for this example. And then the allowable stresses shown here are calculated based on the allowable inputs set in the criteria. So in the criteria, we have allowables for tension, total and sustained conditions at 6 square root of f prime c, and for compression we have values of 0.45 for sustained, 0.6 for total. So we're mainly focusing on these numbers here. Okay, so we're going to now select the tendons and select essentially the span that we want to optimize. So I'm going to go ahead, and when the tendons are marked with these yellow handles, that means they're active. They can be selected for optimization. So I'll go ahead and select this number of tendons. This is 15 strands. If I go to the optimizer tab, we can see that currently the force that we have defined in the model as a total of these 15 strands is 405 kips, and that meets the bottom end of load balancing and also pre-compression, but the program is estimating that we need 893 kips in order to meet the allowable stress condition. So the estimated value shows that for pre-compression, if we select this estimated value, the pre-compression will be 290 psi. The load balancing would be 110 psi, just rounding. However, our estimated stress ratio would be 1 at support. Here, this section cut C, which is the interior support, and it would be also 0.033 at the bottom stress. We were having an issue also at the bottom stress. So using this value would violate the balance loading, but it would still maintain the allowable stress and pre-compression when we look at this individual span. So we'll go ahead and we'll apply that change to the model. I'll go here now to apply. So we're going to mark some numbers here. We have a total force first of 405. We're changing that force to 893. That becomes our new current value once we apply. We're going to apply this change to the model. We're going to apply it as a distributed application over all 15 strands. So the strands currently set to 1 strand are going to be bumped up by an additional 1.21 strands to give a total of 2.21. And once we apply that change, we want to force a rerun of the analysis. So we'll go ahead and say apply again, and the program will automatically reanalyze, and you'll note these numbers change. So once we reanalyze from an FEM perspective, we get a different set of stresses, actual stresses versus the allowable. The current stress now was the 893. The estimated stress now is 1050. So you can see that this is becoming an iterative process that we're using the recycler for. And the reason there's a difference between the previously selected application, which satisfied the isolated span, but it doesn't satisfy the FEM solution. So we have to go through that iteratively. And one way to show that, we'll go ahead and close the optimizer, is if we go back and we redesign the sections. If we recall the overstress at the interior span, and I'll go ahead and turn on the stresses here for the X direction, the overstress was around 1100 psi. We've now whittled this down between the allowable 380 or 379, and we whittled it down from around 1100 psi down to 680. And at the top and bottom columns, we're also moving this down as well. So we would have to continue working through this process to get an achievable design. Now the bottom stress is also being whittled down. You can see the bottom stress here, it now meets the allowable, but at the top and the bottom we don't meet the allowable. And we're really not concerned about these stresses at the top and bottom because they're not being as heavily impacted by the change in the tendon force that are concentrated near this span. But the point is that changing the tendons within this region is having some effect on these outer spans. Whereas if we were to design this frame by frame, we would be completely ignoring that impact from the new PT on these adjacent spans next to the span in question. So let's go back now, and I'll turn my tendons back on. I'm going to re-optimize. So I'll go back to the optimizer. I'll select my tendons again. And remember, the starting point now is not 405. The starting point is the previously selected force, which is 893. And we can see if we continue to accept the estimated force, we're driving our load balancing higher and higher, and also our pre-compression. So we're basically ignoring those two components of the design in order to show how this process is working within the program. So I'll go back and I'll reapply this. We now have another estimated change of 156. So it is reducing. It was previously about 450. Now it's 156. We're adding an additional 0.39 strands to these middle tendons. And I'll go ahead and I'll rerun again and apply. And we can see that now the current value is 1050. The estimated value is 1100. And we continue to go through this process. So I'm going to do this one more time. We're going to apply to the model. This change is delta of 50 kips. The change per tendon is 0.12 strands. We'll go back and apply that. And now the allowable, or the current, is 1100. The estimated is 1115. And we're going to assume that is okay. We're slightly over by about 4% the allowable stress. So we'll just stop there. And the estimated stress now of 1115 leads us to a number of strands. If I go ahead and I apply this to the model, and I'll just say apply, the total number of strands here is 2.76 strands over the 15 strands, or over the 15 lines rather, the 15 tendons. So this is our final design for, let's say, this span and also this span. And one way we can check that is, again, going back and just designing. We'll have to reanalyze here for this. We didn't choose to rerun the analysis, the last acceptance that we made, so we need to reanalyze and then redesign the strips. So we'll select yes. I'll turn the tendon view off, show the support lines again, and the bottom stresses are meeting the allowable. If I go to the top stress, we still have this overstress here based on the FEM result. So this again becomes a cyclical type approach. The difference here between this version and version 2016 is that the program gives you the ability to quickly optimize and narrow in on a result. And we're going to now take this model and we're going to reset the model. We're going to show a different approach in how we could solve this and cut down on the number of iterations and make it a more economical design using the same algorithm or the same optimizer. So let's go ahead and do that. We'll close this, and I'll turn the tendons back on, and I'm going to reset all of the tendons back to one strand. So we're basically starting over. Remember, we left off in the last design loop as 1115 kips for this middle bay, and we're now going to optimize the outer bays first because they're bound by the edge of the slab, and they don't. When we optimize those, there's nowhere for that force to shed at the top and the bottom side of the slab. So this is a different approach to designing the same direction, and this is more economical and more efficient of a design than the previous design. So let's go ahead, and I want to change these tendons back to one strand. So I'll go to the editor, the tendon editor. This is officially called the dynamic tendon editor. So we'll go to strands. We set this to 1. I'm just going to apply and select those tendons, and that changes these all back to 1. We'll go ahead and exit that. And we're now going to optimize this outer bay first. We'll go to this outer bay, and we're going to go back and forth, and then we'll come back to the middle bay. So let's go to the optimizer. And before we do that, let's rerun the analysis to reset our starting point. Given that we changed the number of strands to one strand, we want to make sure we have a new refreshed analysis. I'll open the optimizer. We're going to optimize this bay. Okay, and we have a current and estimated. We're going to go ahead and just apply the estimated. So I'll apply that. And now I'm going to optimize the group down below. We have the same situation, a current and an estimated. I'll apply that estimated, and we're going to rerun the analysis. So the estimated here was 545 at the top. At the top span, it was around 530, and you can see this is much closer just after the first cycle. So we'll now go ahead and estimate or apply this estimation. I'll apply that to the model. I'll go back to the top. And note that I have to rerun in order to make a change to this span. Once these turn blue and they're no longer yellow, they're inactive for optimization. So we'll go back to FEM. I'll close the optimizer for a moment and analyze. I'll reselect my tendons. And this current should be 500 and some, so 532, the estimated is 566. So we're now going to apply that to the model, and I'll go back and rerun again. And we're just toggling back and forth between these two spans to narrow in on a design for the outer bays, then we'll go back into the middle once we're close on those outer bays. Okay, so now we're at 566 and 571. We'll call that good enough for this case. This shows you the current and the estimated. Those are converging. They're almost right on top of each other. We'll go back down to the bottom and do the same thing down below here. Current value is 582. The estimated is 588. So that again is also close enough. So we're going to assume that we leave those alone for now, and we're going to go directly to the middle bay. So we'll go back to that middle bay that we were working on earlier, select those tendons, and if you recall in our first example here, the force was 405, the estimated was 893. So the estimated is fairly close, it's 800 now. We're going to apply that to the model and then rerun the analysis. We now have a force of 800, an estimated force of 925. So again, I'll apply this to the model, rerun the analysis. Again, 925 to 965. I'll do this one more time. And I forgot to check that rerun, so that's okay. We can go into the FEM pull-down menu and just select a reanalyze here. And then going back into the optimizer, I'll reselect those tendons in the middle. 965 and 978. So we're going to stop at this point. We've narrowed each of the spans in this middle, or in the left middle bay, to the point where we're going to redesign the sections and check the stresses. We've gone back and we've rerun the design sections after the latest analysis, and in the design section results based on the FEM solution, we can see that even though the optimizer shows that we've reached our target value for force for the tributaries 1, 2, and 3, we still have overstressed values. And one thing to note here is we're going to take this lower strip for example. I'm going to open the optimizer back up, and we will show the tendons again. We're going to select the lower tributary. So we'll go ahead and select this. And we need to make sure we select the bottom tendon also, so we'll reselect. And we're back here to where we have a current and estimated force. Now, the program, when we are using the optimizer, the program creates the virtual design sections. And we can see that a virtual design cut C is made here. And this is one location where we initially had solved the required force, and now we rerun the analysis, and our FEM results show that it's still overstressed. And the reason for that is within the recycler, or excuse me, within the optimizer, we have this option under settings, which allows us to set the end section cut percent of span. And this percent of span value by default is set to 5%. So when we optimize for this particular cut at 5%, that's actually a different location. It's further away from the face of support than the actual cut along the design strip. So we need to make sure that those are actually in sync. And if I reset this to 3%, which is now the setting, I'll go ahead and update, and I'll select this group of tendons again to optimize. So we'll select the lower tributary, and I'll go over to Optimizer. This is why we have an estimated and a current that are no longer in sync, because I changed the settings from 5% to 3%. The 3% cut, again, is at the exact same location as the design section cut along the support line, which is what we want to do. So we'll go ahead and we'll apply that change again. We have another increase in the number of strands. It's 10% of one strand associated to each of the selected strands. We'll go ahead and rerun and apply. Okay, we're now at 598 and 601. Now along the way, while we've been using the optimizer, going through cyclical increments or intervals of changing the force and accepting the optimizer, keep in mind that at any time, if you want to bypass what the estimation is, you have the ability to go into edit and override these values and manually input a new force. So if the user has a good feel for what the force should be, you can bypass increments or intervals and jump ahead and check an estimated value that you input as the user. That's one option given within the optimizer. So we're going to go now up to the top outside tributary here, and we'll select these tendons. And again, because we changed the percent of the final cut from 5 to 3, we get this gap again. So the gap needs to be closed. We're going to apply that to the model. This is 0.04 strands. We'll rerun the analysis and apply. And we get 578 versus 579 and 580. So essentially that's right on target. It's converged. We'll go now to the middle strip and do the same thing here. And again, we have this fairly large gap between current and estimated. We'll apply that to the model. We have 0.34 strands per line in addition to what's there currently, so we'll apply that and rerun the analysis. Okay, and now we have a smaller gap. We're going to run it one more time. And we're going to accept this. So we might have a slight overstress again at the middle, but we'll close the design at this point. I'll close the optimizer. I've rerun the analysis, so we just simply need to go back and design the design strips. We'll select yes to save the design strips, and I'm going to turn off the view of the tendons. Turning on the view of the design cuts, the top has been solved. This is 338 versus 379. The bottom has been solved, 341, and the middle is 383 versus 379. So this is roughly right at a ratio of 1 for the stress utilization. If you have any questions about Optimizer or the use of tendon modeling and design in AdaptFloor Pro, please feel free to call us or email us at support@adaptsoft.com. You can reach us also at 650-306-2410. Thank you.